co-founder and CTO of Cusp AI. For people not in the know, can you give us a quick intro, quick pitch? What is Cusp?
Yeah, Cusp AI is the easiest way to think about Cusp AI is a search engine for materials. And so the way I am so fascinated by molecules and materials is that there is a sheer infinite amount of materials you can possibly make, and each one of them has very interesting new properties. And so humanity and nature have actually made only a tiny amount of those molecules. And so we have seen only a slight, small sliver of what's possible. And with the search engine, you can actually tap into the full potential of all possible materials. So I think in the future, we'll find all sorts of crazy materials out there that will change our lives, basically.
Yeah, I'm really excited to see that, and I personally really believe in it. But why now? You've had such a long and successful academic career. What has made you leave and join the startup world in this environment?
Yeah, so when you get a little older, you also get a little more worried about, in the world that your children and your grandchildren will live in. So if you think about the projections for climate change, they all say around 2100, we want to keep it in 1.5 degrees or 2 degrees or 3 degrees global warming. And if you think about what 3 degrees means, there's actually already quite a huge impact. But you also think that your children might actually make it to 2100, and your grandchildren will certainly make it to 2100. So they will live in that world that we will leave behind. And if you dig into it, I think it is really, it's happening. There's very little uncertainty that this is happening. And I ask myself, how can we change this? Well, I can try to convince, politics to make it more expensive to emit. I'm not a lobbyist, so it's not going to work for me. But I can actually build technology to try to reduce the cost of alternatives, like green solutions. And this is why Cusp AI was born. I could add to that as well that we are on the cusp of a technology change where AI is going to change the way we do science. And that is also a very exciting time. I have a background in theoretical physics, and then I changed to AI and machine learning, very small models at the point when I changed in '98. And now these two fields are coming together, and that creates very interesting new scientific challenges.
So I hope to live to 2100.
You should.
And if I get there, what are you working on now? What are you seeing from the platform that you're building that might enable that? Is there anything that's really excited you?
Well, I would say we haven't seen superintelligence or anything like that. It's not emerging like an AGI coming out of it. But what you do see is that you have a control over matter, and I think this is what humanity has always done in some sense. It's really tried to control and manipulate matter to do the things for it and sort of help technology and drive humanity forward. And it's just extremely exciting to design a material in a computer that no human has ever seen before, that has never walked the earth. And then you design it, and then you make it, and then it's there, and it has the properties that you predicted. And it gives you a very, powerful feeling. It's like, okay, if I can do this, I can now make materials that create better batteries or can capture carbon out of the atmosphere. I think that is a very powerful feeling.
Yeah, you've manifested.
Yes, I've manifested. That's very true.
Something that we talk a lot about in machine learning, but usually on the LLM and image side, is scaling laws. How much better do these models get as they get bigger? Do you think that those same scaling laws apply for AI for science models, or is it just a fundamentally different thing?
No, they apply just the same way. I think it's an inherent property of machine learning models that as you start to scale the amount of data and you scale the amount of compute as a result of that, the models keep improving. And we've seen that a little bit in our collaborations with Meta, where Meta generated 200 million or 300 million quantum calculations, and those calculations were used to train models. And so those are data sets of a size that start to approach something where you can see a scaling law. It is not LLM space where you can download the entire internet, where the amount of data is way, way larger, where these scaling laws are much more prominent. And so in that sense, the two fields are a little different in the way that it's much more expensive to generate data. You either do experiments, which are very expensive, or you do quantum calculations, which are also expensive, but it's a little bit less. And so to expand these data sets, you really need to throw money at it, and that means that these data sets aren't so large. Also, I would say people aren't really sharing their data very much. Right? That's the other thing that we want to talk about maybe.
Yeah, that's a huge problem. And I think a really interesting thing going on in AI for science in general, and this is true of pharma as well, is that a lot of people are generating the same data over and over again for the sake of privacy and for the sake of competitive edge. But a lot of that means that we're wasting a lot of resources doing the same things twice. But speaking of scaling, data, models, all that, you guys are scaling too. You just raised $100 million for your Series A, very impressive achievement. But something that really struck me is that you have sort of non-traditional funders. I'm thinking Temasek and Samsung, Hyundai, not typical names in this space. How did you choose them?
Yeah, so actually Temasek came to us more than we came to them. In a sense, we weren't even quite ready for a Series A. We had enough on the bank at that point. But they came to us prematurely and they said, maybe it's a good idea to start now. And they were right. I would say competition is heating up. There's other companies starting very fast behind us. And so Temasek is the Singaporean government investment fund. And they are, many people have PhDs in material science and chemistry. And so they've been incredibly helpful actually also on the technical side, amazingly. And so they've introduced us to lots of opportunities around Singapore and other places. Hyundai and Samsung are strategic investors. And of course we chose them in the hope that we could do projects with them together.
Is there anything in particular with either company that you're hoping for?
We are actually working with Hyundai at this point. And so we have a project on fuel cells. The fuel cell is kind of the inverse of an electrolyzer. That's kind of an interesting little factoid that I learned, where one of them generates hydrogen and the other one uses hydrogen to generate power. And so that's a beautiful example of a sustainability application that we at Cusp really like to work on. If we improve the fuel cells, we can drive cars more sustainably and greener.
Awesome. Something that is also really interesting is all of these groups are Asia-based, which I think really just goes to show how international and worldwide of a mission this is. As you know, Hugging Face is really involved in trying to engage the developer community and making sure that people all over the world are represented and can participate in building the future of AI, science or otherwise. How do you see the role of open science and open source in machine learning for science?
Yes, I think open source is really important. By the way, NEA was also on our cap table as a major investor. That's an American-based company. But I would say open source is incredibly important, and we should, and Hugging Face is a great example of facilitating the open source part. And whenever we get data, we should share as much as possible. But of course, there is, for a company, also a bit of a tension. If you give away, data is the moat of your company often. It's quite easy to, catch up with models and algorithms. With compute, you can just buy it. But data is harder to get, and so that is part of your moat. And so then the tension becomes, how much do we want to help the community forward? Because we do want to do this, and in our project with Meta, we actually did open source everything we did together with them. So we really want to do that, but you also want to keep some data for your own model so that customers can come to you, they preferentially choose you to work with you. Because if you build a company with all the great intentions of saving the world and then your company folds, you're not making any impact either. So it's a balancing act.
Yeah, of course. And there are, as you say, big other players in the sort of AI for science space. Meta, NVIDIA, DeepMind, but also new startups, Periodic just announced a big funding round.
Yeah.
How do you see collaboration and competition in this space? Or is everybody going off on their own adventure?
Yeah, it's an interesting dynamics. I think we can take an example of the semiconductor space in which we're also operating. In the semiconductor space, there is sort of pre-competitive labs where, like IMAC is an example of a pre-competitive organization that works with all the big semiconductor players. And at some point, when it gets to the phase of commercialization, they split off and do their own thing. And so they're creating technologies together and they're creating data sets together that benefit the whole field and drive the whole field together. So I think that's something that we should do in our field as well. So we think about what is pre-competitive, we work together, and then at some point we find our vertical, we think we are good in this particular thing, with this particular material class, and we will defend that one with our moat.
Yeah. There are so many interesting problems to work on, and you've discussed a whole bunch of them already just in this talk. I'm thinking also of a collaboration you guys recently announced with Chimera to try to remove PFAS, or forever chemicals, from the water, which is something we all suffer from. How do you think about which projects to work on? How do you spend your time? How do you prioritize?
Yeah, so when we started Cusp, it was clearly with a goal to help solve some of society's biggest problems, and those could be environmental, helping the energy transition, and removing carbon from the atmosphere, and cleaning up the environment. So that one was very well aligned with sustainable environment. And so that was a simple one for us to catch on to. We could develop our platform together with a chemistry company that would help us also understand the chemistry better, and together in a deep partnership we built new materials for PFAS removal. Now there is an interesting tension again, so it's a bit of a balancing act. If you pick those, you cannot just completely kind of a charity where you say, oh, let's just pick the nicest project that would help the world the most. Because in many places there isn't an actual strong market. Like carbon capture looked like it was becoming a strong market, but with geopolitical things that are happening, that market isn't developing as fast and as strong as we want it to be. And so you sometimes also have to pick topics where at least you could say it's neutral. Like semiconductors, I would say that's at least a neutral technology, although you could argue it does power progress and wealth in the world. And so we also sort of have a portfolio, a balanced portfolio of working problems that we sometimes even fund internally, where we can help the world forward, and we often open source. And there is project where we can make serious money, so to keep the company afloat. And then there's other interesting ethical things to make. If you want to truly build technology that takes carbon out of the atmosphere, sometimes you have to work with the big oil companies, because those are the companies that have all the technology and the funds to do it. And so how do you put those things on a scale? And so you're constantly asking yourself, what are the ethical implications of what I'm doing here? But I don't know, it's a fun game as well.
So I'm going to put you a little bit on the spot here, but how do you adjudicate that? Is it gut feeling? Is it research? Is it debate with your team?
It's definitely debate with our team, so we have a very open culture. So we actually will soon have a debate within our team about certain companies that we have been approached by, and then we have the team is small enough for all of us to contribute. We have invited one of our advisors to lead, or actually two of our advisors to lead the discussion, and then we are open-minded. We just think, so we put everything on the table. If we don't do it, these are the negatives financially. If we do it, we have to live with the idea that we are doing something that might not always help the world in the right direction. And so we have to balance these things, and then the outcome of that will determine what we do in the company.
Very cool. Big throwback to the Socratic method for those who remember their intro to science. We talked a lot about data, but what beyond that, maybe, do you see as the bottleneck to achieving the vision that you're talking about?
So data, okay, I think right now there's two developments in this field. One is computational, and the other one is self-driving labs. And so these are labs that would do very high throughput experimentation and that sort of guide themselves in doing the right experiments. Putting these two things together is a big challenge, and I don't think that one has been solved. But it's solvable, and it will be solved in a few years, I have no doubt. That's actually not rocket science, it just needs to be done. What is rocket science, in my view, is how do you get it in the real world? And this is not something I anticipated to be the most important bottleneck in the process. But how do you get companies to buy your stuff, to change to invest so that your material is going to be produced at a ton scale? To maybe invest in their processes and their manufacturing lines to do that, to change that in light of that new material, and how do you get it to the people and then users? So those are actually a completely different set of problems that come that we have to think about very hard in order to make the actual impact that we want to make.
100%. I don't envy that challenge, but I'll look forward to seeing how you handle it. Before I turn to audience questions, just for the future, wax poetic for us, what do you hope to have achieved with Cusp in, say, 10 years? If you could make one discovery, what do you hope it would be?
If I make one discovery, I just first want to say how hard the discovery is. Every prognosis that people make in order to get all the carbon dioxide out of the atmosphere basically says that after 2050, when we have to be carbon neutral, we have to pull carbon out of the atmosphere using direct air capture or techniques like that for a century at about half the rate that we're pumping in it now. So that's 20 gigatons a year. If you compute how much energy you need to do that, it's mind-boggling. And so that technology does not exist, but the fate of humanity relies on it. Not to be over-dramatic, but that is the situation, and people don't actually think about it too much. So if you can make one discovery, that is the technology to remove carbon dioxide from the atmosphere at a reasonable price.
And we should all invest in fusion.
Fusion is great too.
Handshake on that. Any questions from the audience? There are people with mics around.
Hi, Max. My name is Chen Yu, and I used to work at CATL, so a lithium manufacturing company. And now I'm at MetalSub. We're a software company that digitalizes how the raw material is traded in the metals mining industry. So my question is specifically on what kind of projects do you guys currently have for either battery materials or in general metals mining industry? If you could disclose, I'm not asking for any confidentiality.
Yeah, I see a future customer. That's great. We should talk after the meeting. We do. So I cannot talk about actual things we do because it might break NDAs. But we do have a project in clean mining, so we can definitely talk about that. We also have a project in fuel cells, and not yet in batteries, but we are talking to customers definitely also about batteries, electrolytes, better catalysts, and these kinds of things. So we actually have a quite broad portfolio. Our platform can handle many kinds of materials, and we'll have to be retrained. So there's certainly a bit of an effort to apply it to a particular material class. But we like to do this in a deep collaboration with the company. But as long as you can simulate the material using the laws of physics, so you need to know the laws of physics, and the material shouldn't be too quantum mechanical, because then actually it's going to be very hard to simulate to get data. If it's simulatable, we can accelerate it with machine learning tools, and once we have accelerated it, we have unlocked search, and so that we can improve the material. So those are the sort of boundary conditions. I'd be very interested to talk to you about problems that you're interested in. So let's meet after the talk.
Hey Max, and thank you for the talk. My question might be a bit technical, but it's about scaling laws. So the current LLMs we're using based on the foundation models, the number of parameters are increasing every year, and also the data required to train them. So my question is, after some point to train an LLM, the number of data in the internet is not going to be enough. So when we hit that point, and I don't think it's going to be too late, what needs to change, and which direction we should go?
Yeah, so it's a bit slightly outside of material science, I think, your question.
Yeah.
But let me try to answer it anyway. I think at that point, so I think we're not quite running out of data yet, but at that point, I think we can start to do simulations, and in that way, it is interestingly connected with what we do. So in order for us to generate data, we simulate physics. So in order to generate more data for LLMs, you can simulate with the laws of physics, and sort of simulate video by using basically good generative models or other simulators. So that way you can sort of generate artificial data in a much larger amount. I think the next step will probably be when we put sensors everywhere. So robotics, I would imagine, like also in cars, but also just robots, they have a lot of sensors in them, they interact with humans, and that, besides it could be a very useful sort of platform, it's actually also a vacuum cleaner for data that gets pumped up, right? And so I think we'll see robotics play this role of also generating a lot of data out of the real world. Whether that is a good idea or not, I'm just leaving it here now. Whether privacy is going to be an issue, but I think that's where we'll find new ways to generate lots and lots of new data.
Hi Max, I'm Henning. I'm a co-founder of a company that does very similar stuff that you do. We founded but with a clear focus on metallic materials. And we indeed focus on the latter part of it, while knowing that material and process interact with each other. So, if you put an aluminum alloy into a Cusp process, it behaves differently than in a laser particle fusion process, just to give you an example. And of course the ramp up as well. How do you incorporate in your platform? That's number one question. Number two, whether you provide the platform or you provide the service. But question number one is, how do you incorporate the processes to make it industry ready and not keep it in the laboratory?
Yeah, this is a great question. So what we have is a process model. So that's you should think of the model that we use to optimize against as a full digital twin of the actual physical process in which this lives. This is not just simulating the microscopic processes of the atoms bouncing around and the quantum mechanical processes, but this goes through all the scales. And so, for instance, for carbon capture, we actually model the rig in which the material sits and needs to, and then you blow air through it, and how that process and how that happens. That's all modeled with PDEs, etc. All the way to techno-economics, right? So what is the technical economic sort of analysis of bringing a new material out there in the world, and life cycle analysis? What do how long will it live, and what do you do once it's out of commission, right? How do you remove it? So all of these things ideally need to be modeled, but it's also very expensive to do it for every new vertical. So it's kind of, you need quite a few people to model that for every new application. And so typically we like to do this with the partner. So if we go to a customer, all that knowledge typically already sits with the customer, and we hope that they can provide kind of this last layer of more macroscopic modeling for us. Sometimes we do it ourselves, or there's some publicly available process models, for instance for batteries, that you can also use.
Awesome. I think we're at time, which means that everybody gets to have dinner. So thank you so much, Max. It was great to chat, and thank you all for being here. made it special.
Thank you, Georgia. That was very nice.
Thank you so much to Max Welling, Cusp AI, and Georgia Chang from Hugging Face. So we're going to reset the stage. Thank you so much to all of our speakers to date. We're going to be having a quick 15-minute break now until 4:40. We're going to finish with a bang, so make sure you're here for 4:40 on the main stage. Enjoy your coffee. See you in a bit.